Hello, I hope all's well with you. Today we begin with matrices. So, in the previous lecture, when we were doing vectors, we denoted vectors by lowercase bold letters. Today, most of the time, when we talk about matrices, we'll try to distinguish them from vectors by uppercase bold letters. That's not always going to be true, but mostly true. A matrix, as you might remember, is a two-dimensional collection of numbers. Here's a matrix X. The first subscript is number of rows, N, Nancy. Columns are K, kangaroo. And you'll notice that I put subscripts here. So first row, first column, first row, second column, first row, kth column. Down here you have nth row, first column, and so forth. So you can tell by the very last element down here how many rows and columns this matrix has. So it's understood that you know how to use notation n by k rows and columns. Since you start doing programming very soon, econometrics, whether you use VBA or MATLAB, you have to some often call out particular elements. So the notation here, lowercase xij, stands for give me a certain element in this matrix. So for example, if you want to say give me the x56, you would extract the element in the fifth row, the sixth column. Is useful for this, well, in this lecture, one of the things that's going to be really important is to view matrices a little bit differently than what you saw in undergrad. So here's an n by k matrix, a collection of numbers. But if you actually think about this, each row is a vector unto itself. So you can imagine that one way to look at this matrix is as a collection of row vectors. And now the question is, how many row vectors are there? Well, there are n Nancy rows, so there must be n Nancy row vectors. Well, which dimension are they sitting in? Since the number of columns is k, you have n rows vectors, each of which is sitting in space Rk. Right? And by the same token, you have k column vectors, right? Each of which, if you think about this, here's one column vector, second one, and so forth, each of which is sitting in Rn for Nancy. So an example, just a simple collection of numbers. This could be anything. So here you have 4 rows, 5 columns. And if somebody wants to extract the second row, third column, there you have it, x23. And now you have the third row, second column, number 2. Let's spend a little bit of time on econometrics. I'm probably going to deviate from last year's lectures by, at some point very soon, doing matrix algebra according to what you'll need for ECHO 2408, which is econometrics. And this is especially true for MFE students. You're going to take econometrics with Lord Master Angelo Malino, and Angelo Malino expects you to know matrices, at least seen it once. If you're not an MFE student, even then you should pay attention to what I'm about to say. In this course, the most dangerous part is not the math, it's the stats. And that's because what I do in stats is I try to spend about 5 lectures trying to explain under what circumstances you can write down a linear regression model. Back in undergrad, most people tend to BS. Oh, I think there's a linear relationship. Or let me draw a straight line through a scatter plot. Yada, yada, yada. So we'll see what are the rigorous conditions under which one can say that there's a linear relationship between y and x's. And of course, you know the word linear here does not refer to linear in pluses here. It refers to linear in parameters. You should review your econometrics. What's extremely dangerous in econometrics, especially if you are the young generation, you, tends to study not from textbooks like I did back in 1625, but YouTube. YouTube is the curse of education. Everything's gone downhill since YouTube has shown up. Because the trouble with YouTube is you would be watching somebody's lectures on econometrics, and their notation could be slightly different than yours. Here's what I mean. You have a cross-sectional model, and now let's say you have n observations. That's fair enough, n individuals. The trouble is that you'll notice that the way I write this down is I have an intercept, which I call beta 0, and I have x's. These are your independent variables. And in my model, there's 1x, x1, x2, k x's. So the total number of x's in the pure sense of being x variables are k plus the intercept. Now, of course, some authors will say the x's refers to the intercept as well. So the question is, do I have k x's according to over here plus an intercept, or do I have k x's which includes the intercept? So have to be very careful, because if somebody said there are k right-hand side variables including the intercept, then this would not be xk, this would be xk minus 1. And you really have to be very sure when somebody says there are k independent variables, are they k with the intercept or without the intercept? So in my version of stats and econometrics, there are literally k x's, these are as in variables, and an intercept. So the total number of right-hand side variables is going to be k plus 1. Now, of course, you know that, just as beta 1 is the coefficient corresponding to observations on x1, just as beta 2 is the coefficient on observations corresponding to x2, beta 0, the intercept, is the coefficient on quote unquote data corresponding to number 1. So behind the scenes, you can imagine a, these are your y observations for n right, individuals cross section. Here's your 1, 1, 1, 1, 1 for n individuals. Here's your x1 for n individuals, x2 for n individuals, etc., etc., etc. Now I'm jumping ahead and I'm assuming that you remember matrix multiplication, but you should realize that this is a matrix Y is equal to X, this whole giant thing is X, times beta plus the quote unquote epsilons or error terms. The dimension of Y, of course, is n by 1, Nancy by 1. The dimension of X, of course, is tricky now. It's k plus 1 rows, right? And then, actually, no, sorry. It is n rows. Let's see how dangerous this could be. It's n rows and k plus 1 columns. And of course, how many variables do you see here? You actually have k plus 1 rows and 1 column. And of course, this is n rows and 1 column. Typically, some people write matrices like this in econometrics. Others do it this way. Others will do it this way. So you should be prepared for deviations in notation. In Wolfram, you can easily make any matrix by typing out using this syntax. So I'll leave it to you to do this. It's a good idea to do this now, because next week all hell breaks loose. So you want to start using Wolfram right now and not next week. Now, you used to do vectors, well, lecture A, and now we're in matrices. Now we have to worry about slight subtleties. When I was doing a vector, this could have been a 4 by 1 vector. This could have been a 1 by 4 vector. And if I asked you to do an inner product of the first vector and the second vector, it didn't matter whether you took this quote unquote vector and inner product this one, or you start with this one and inner product that one. That's because you were in vectors. In vectors, if you remember, we didn't care whether you wrote it as a column or as a row, because it didn't really matter at that point, right? But now it does matter, and you'll want to see why it matters. So coming back here, if I now interpret this as a matrix and not as a vector, then this is a completely different matrix than the one where I simply take the column and flip it and transpose into rows. So one more time. If these are vectors, if you're carrying out operations and so forth, it doesn't matter whether you work with the column version or the row version. Or if these are matrices, it does matter whether you are now working with the column or the row version. And you might be saying, well, wait a second, why does it matter? And how the heck would you know whether you are in the world of vectors or in the world of matrices? Well, it's one way to appreciate when you are working with vectors as opposed to matrices, and why it does matter whether you work with columns or rows is because you're about to show that a matrix always represents is a one-to-one representation of a linear vector function. That means what? Well, let's go back and revisit linear functions, and let me remind you one more time. In vectors, you are perfectly okay going with working with a column vector and a row vector. And notice I didn't have to say transpose earlier, but now we do need to worry about matrix X being fundamentally different than its transpose. Let me sort of jump ahead in slide. Okay? When you hear the words linear vector functions, or linear functions, linear lines, and so forth, the equations, especially those of you who grew up in North America, even though I was born in North America, I didn't grow up in North America, but North American schools love linear equations, something along the lines of m plus bx or b plus mx. I don't know. Things like this, right? And you are hardwired by your, you know, previous training to always, when somebody says give me a linear function, the first thing that probably pops into your mind is your head is an intercept plus a slope times x. But you're in grad school. Things are different. In grad school, a function y in terms of x, remember a function is an engine, a machine that takes x's as the input and spits out y or y's as the output. What's different now is that you may have several x's as the input, right? You're used to having a single y as the output, but now in vector functions, you can have several y's as the output. So you have a function, just like any old function, some y's expressed in terms of x's. The domain is Rk, which means all the x's must be sitting in Rk, and the range is Rn, which means all the y's are Rn. Is this y is Rn, that x is Rk. Okay, the inputs are Rk, output is Rn. Such a function, an equation, is called a linear function whenever the following two equations are true. And I really hope that the use of y here, which I did by the way on purpose, doesn't confuse you. This y is not the same as that y because now you're reminding yourself that it's notation, so you can use any quote unquote variable to denote a set of inputs. So as long as these two properties are true, so this is it will be a linear function. This is what? This says give me an equation like this one. Wherever you see an x, if you were to now put an x plus y, the answer you would get is the same as this equation with just x plus this equation where you took the x out and replaced by y. So putting in x plus y over here would be the same answer as this thing with an x and this thing with a y. And you can see that if we in fact carry this calculation out, that's not going to hold in this case. The second thing that must be true is that wherever you see an x, if you multiply it by a number, the answer that comes out is the same as taking this equation and then multiplying with a number. If these two properties hold, it's a linear function. If any of these properties are violated, it's not a linear function. You should carry out these two operations and check for yourself this is in fact not a linear function. So abandon all notions of straight lines that you used to have. No more intercepts plus slopes. Right? Goodbye. In what sense does a matrix represent a linear vector function? This gives you now a deeper insight into how a vector is not the same as a matrix. Here's a bunch of equations. Notice I have two x's, see, x1s and x2s, but three y's. So I'm going from R2, 2x's, to R3, 3y's. So the domain is R2, the range is R3. And why does how can I represent this by a matrix? If I slightly rearrange this, you'll notice I say, aha, 3x1 of course is 3x1 plus 0x2. Now I'm jumping ahead, I apologize. Assuming that you remember how to do matrix multiplication, everyone agrees that I can rewrite this as a, right here, the matrix Y is equal to this matrix multiplied by X. So your Y is equal to A multiplied by X, and this is a linear vector function. In fact, you should carry out these two operations on the previous slide and verify that this is in fact a linear vector function. So you've just seen that this matrix uniquely represents this particular function. Which function? The number of rows are 3, number of columns are 2. If the columns are 2, it must mean that your domain is R2, 2x's, and your range is R3, 3 rows, right? So in general, when somebody gives you a matrix with n Nancy rows and k kangaroo columns, you're literally describing a system of equations that goes from our k domain to our n range, k x's, n y's. For example, here is 1x only, so the domain is R1, but there are 4 y's. So you now have a linear vector function that goes from R1 to R4, uniquely defined by this matrix A, 0, 1, 10, 5. It now gives you this y, these y's, in terms of that x. So this is that vector that you saw sometime back, the column vector. But notice if I flip it, transpose it, I'm then describing a fundamentally different system of equations. Because now what I'm doing is, instead of describing a system of equations where I'm going from R1 to R4, I'm actually now, by flipping this quote unquote vector, describing a system that goes from R4 to R1. And you can see that by here, this matrix B, 0, 1, 10, 5, now describes a completely different system, going from R4 to R1. So you can see why, even though in vectors it didn't matter whether you worked with column or row versions, in matrices it does matter, because a matrix is describing a linear vector function from the domain of R, which is the column, number of columns, or k, to number of rows, or n. So let's remind ourselves that these are now matrices. They now describe linear vector functions. Again, in previously it didn't matter which way you work, but now it does matter. So these are now matrices. Behind the scenes, they fundamentally are describing some vector function, some y's in terms of x's. And I really encourage you, including the math majors, to write down a system of equations that represents, just sort of, so that you understand what system of equations these matrices are describing. And while you're at this, you might as well compute these animals. Now, basic stuff. How do I know two matrices are quote unquote equal? They must have the same dimensions, number one, and each element must be the same. So you can't have two matrices with different dimensions be the same as each other. And even if they have the same dimensions, each element has to be the same. For one element 1, 1 must be the same as 1, 1 over there. So you can see literally element by element by element. These two matrices are not equal because you can see by element, they're not the same. And if I want these two matrices to be equal, then it must be the case that X must be 7. Square matrices are really important. Uh, by definition, a square matrix is one whose number of rows is equal to number of columns. And so what we'll do down the road is, instead of saying 2 by 2, if it's a square matrix, we'll simply use x2. It's understood that anytime you see notation x subscript n, you are now working with a square matrix with n rows and n columns. Here's an example right here. A square matrix is symmetric if the off-diagonal terms are exactly the same. For those of you who have not done lots of math, One of the reasons I'm doing this lecture is because you really need to start understanding what these expressions mean. Mathematics is a language like any language, and what practice makes perfect. So you should see what this is saying. This is saying when is a matrix symmetric? When the when the element in the ith row and jth column is the same as the element in the jth row and ith column, right? As long as those I is not equal to j. Why did I have to say this? Think about this. If I had not said this, right? If I had, right, then then it would be kind of, right. Then you'd be saying something trivial. If you let I be equal to j, all you'd be saying is x11 is equal to x11, which is a trivially obvious statement. X22 would then be equal to x22. So to remind the reader that you're in fact talking about off diagonal terms being symmetric, you do want to put this I not equal to j. So for your convenience, notice that even though the diagonal terms are different, right? You only want, if you have a piece of paper and you fold the matrix that way, all the off diagonal terms are the same. 1, 1. So the first row, second column is the same as second row, first column. First row, second column, same as second row, first column. First row, third column, same as third row, first column. Second row, third column, same as third row, second column, right? Jumping ahead, you should review multivariate calculus. You may remember Young's theorem. The Hessian matrix is this matrix of second derivatives. And you will notice that over here in this matrix, I did not say fn1, right? Because by Young's theorem, the f f the second derivative of, let's say, ij is the same as second derivative of ji. So these off diagonal terms are always going to be the same. Traces. The trace of a square matrix, you cannot do this for rectangular matrices, is defined as the sum of the diagonal terms, CII. So it's understood that you're summing up the diagonal terms. So here's the trace of this matrix, right? Sum of the diagonal terms. Here are two examples, right? This one is a square matrix. Here's the sum of diagonals. Here you can't do this because it's not a square matrix. Here's a diagonal square matrix. The word diagonal means that all off diagonal terms are zero. We don't know anything about the diagonal terms. They may be zero, not zero, nobody knows. But the off diagonal terms are definitely zero. See over here. So in this course and other courses, we will express diagonal matrices as follows. So in a diagonal matrix, I only really need to specify the diagonal terms because I know that all off diagonal terms are going to be zero. So on the test, which is coming up very soon, on a Friday, of course, grad school, U of T, we will give you expressions like this. You should be able to then you should be able to back out the fact that all off diagonal terms are zero. Just in passing, we will need this for econometrics. You can actually have lower triangle matrices where all terms on the diagonal below are possibly non-zero, but all off diagonal terms above the diagonal are zero. I really urge you to understand why I wrote these things this way. Why did I say J is bigger than I over here? And why do I say upper triangular matrices J less than I over here? Spend some time, make sure you understand this. We will put a question on the test to test you on this concept. Some other matrices. Well, the zero matrix, which of course can be written this way, and the identity matrix, whose diagonal terms always consist of one. So it's a uh, diagonal matrix, right? So all the things are ones over here. All of diagonal terms are zero. Now operations. So just like numbers, I need to now define products, summations, etc., etc., etc. Let's do scalar multiplication. Let baby t be a number, x be a matrix. If you want to multiply a number and a matrix, all you do is you multiply each element of that matrix by that number. Here are two examples. Here's an example, and this is, of course, if you want to see how this is done in Wolfram Alpha. You want to add or subtract matrices. Before you can do so, they must have the same dimensions. Otherwise, it's impossible. So they both must be n by k, n by k. So literally what you do is, if you're adding, you will add element by element, right? X1, 1 plus Y1, 1. And if you're subtracting, you take the first one, subtract from the second one, element by element. It's not rocket science. Here are some examples. I've given you X and Y's, and as an example, here's X plus Y, and here's Y plus X. And notice that in general, it is true. You may want to prove this using, general notation. But when it comes to matrices, X plus Y is the same as Y plus X, right? Um, and here's an example of X minus Y. And of course, you can figure out Y minus X on your own, right? So now comes hell, matrix multiplication. So in addition, matrix, when you add things up, X plus Y is the same as Y plus X. But as you might remember, X times Y is not necessarily the same as Y times X. But before we go there, let's jolt your memory a little bit. If I want to multiply two matrices, they have to be quote unquote conformable, right? Able to be multiplied. And the way it works is, here's matrix X with Mary by kangaroo dimensions, and here's matrix Y with kangaroo by Nancy dimensions. For you to be able to multiply the first matrix columns have to be the same as the second matrix rows. So k columns of the first matrix, k rows of the second matrix. So these two things have to be exactly the same. And what will come out, what animal spits out, eventually will be a matrix with m rows and Nancy columns. So first make sure the k's are the same, and then you know what's going to come out is a matrix with m rows and n columns. So if you know when you multiply these out, provided these are conformable, we know that the end result is going to be a matrix by this many rows and that many columns, which again you understand that this matrix X represents a vector function from Rk to Rn mother. This one represents a vector function from Rn Nancy to Rk, right? Um, but this one represents a completely different linear function from Rn Nancy to Rm Mary or mother. How do I multiply? I'm going to abuse notation and say to my sort of, it's not the world's best notation, but here goes. Notice how the first matrix, you can think, one way to think about this is it consists of M Mary row vectors. See, 1, 2, 3, all the way to M. And the second matrix Y consists of how many column vectors? K column vectors, right? 1, 2, and so forth. So remember, these are each of these row vectors is in Rk, and there are m of these mother, and each of these column vectors is sitting in Rn, and there are k of those. The rule for multiplication is you take the first row vector in X and inner product with the first column vector in Y. I've done that for you here. Then you will take the first row vector in X, inner product with the second column vector of Y, etc., etc., etc. And as you keep going like this, so basically what you're doing is your first row consists of the first row vector inner product of each of the column vectors in the Y matrix. You can see it's over here like this. So if you follow this format, that's how you do multiplication. And now you kind of want to be a little bit careful. How do I know that I can do this? Don't I need to remember something from lecture A? Can I just take any vector x and inner product any vector y? Well, no, you can only do inner products if the quote-unquote number of elements in x are the same as the number of elements in y. But voila, that's exactly what you have here, right? Because each of these row of vectors was sitting in dimension k, each of these column vectors was sitting in dimension k as well. That's why you need to check if k and k are exactly the same. So you can in fact carry out these inner products because each of these row vectors and column vectors have k elements each. And the answer is going to be a scalar, a number. So you can imagine something like this. Someone gives you a matrix X, asks you to multiply matrix Y. You know that this is a conformal 4 and 4 match. And now you notice that the second row, fourth, fourth column element is gotten by taking the second row vector in matrix X and inner producting it with the fourth column vector in Y. Right? That's how you get this. I strongly urge you to work out these examples using this inner product notation, and just so that you truly understand what's going on. I'll give you two examples that show that x times y need not be the same as y times x. Agree? Right. Now, this is done on purpose. This is to remind you that, many of you I've heard from Tommaso are asking for detailed solutions. Uh, Listen, you need to grow up, and you're in grad school. You're not in just any grad school, you're the best econ department in Canada, right? Definitely top 20 globally. So you're obviously not going to spend your graduate school working in numbers, which are for babies, right? Um, you're obviously going to work with general models. So it's really important that you start to get used to this notation because you don't want to wait 24 hours before the test and then try to figure out what in God's name these things are. So I urge you that remember that these are row vectors, column vectors. I've done that for you here, right? If you now expand, if you actually carry out these operations, which I've done for you, what a nice guy that I am, right? You will notice that here's the inner product of the first row vector of x, first column vector y. I've done it for you. You really want to go through these notations and make sure that these are right. Maybe I made a mistake. I'm human after all, right? Here's this expression right here. So you want to make sure these things are right. And then what's really important is you want to go from these expressions to those expressions. So this really requires having a very solid grasp of what you're adding from until to, which subscripts are fixed. You can see that the number 1 is fixed here and the number 1 fixed over there. And where's the index moving? I will 101% put a question on the exam that tests your understanding of how to work with expressions like these. Can you go from here to here? And can you go from there to there? Do it. Now, matrix multiplication. I already know that x times y may not be the same as y times x. Got it. What about things like this? Notice in this example, x times y is the same as x times z. Now, had these been numbers, you would have quote unquote crossed out the x's and you would have then declared that y is equal to z. But that's not the way it works in matrices. Notice that even though these two things are exactly the same, the end results, y and z are different from each other. So it is possible to have this result even though y's and z's are different animals and different creatures altogether, which would not have been possible in numbers. Here, notice that even though the matrices x and y are individually not equal to 0, when you multiply them out, they are equal to 0. This is what kind of witchcraft is going on here. And now this is begging to be a test question. I can't even believe I'm giving you a hint right here. Like, can you tell me in very general terms when you will have a matrix X that consists of numbers other than 0 and a matrix Y that consists of numbers other than 0? What must be true for X times Y to always be equal to 0, right? You can use the machinery of lecture A to state a general result. Something must be true. Not only in terms of I'll give you a hint, not only in terms of inner products, but in terms of orthogonal vectors. There's your hint right there. Operations and some rules. Assuming that you have the right dimensions, all that stuff, you want to go through this here. Nothing really, but you just have to be careful here that you can't suddenly, like, you can't just say A times B and A times B over here and then down the road say B times A. It's not the same, right? So you want to work through these things. Here are some homework questions. Now we do something even more dangerous, and this is especially true for the math majors who tend to fall asleep when we talk about multiplication. You already know that a matrix is a unique representation of a linear vector function from Rk to Rn. Well, what about multiplication? Let me try to motivate you by a simple example. Supposing you're given a bunch of z's in terms of y's. These could be demand curves, for example, right? Uh, and then you're given the y's in terms of x's, right? So you're given z's in terms of y's, and in turn you're given y's in terms of x's. Somebody says, I want you to express the z's ultimately in terms of x's. Now, one way to proceed is you could yawn and say, okay, you know what? It's so easy. What a nice guy. He gives me y1 already in terms of x's, so I'm going to sub y1 here, point. He gives me y2 in terms of x's, put that in there. Give me y1, stick it in terms of x's right there, and so forth. And then you spend the rest of your life simplifying, rearranging terms, making mistakes, blah, 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 and one day you get the answer. Okay, you could do that. But what if there was an evil, evil man, let's call him Hussain, who then gives you the following question. He gives you A in terms of B, B in terms of C, C in terms of D, D in terms of E, you get the point. And ultimately Y in terms of Z. 26 equations. And he wants you to express A in terms of Z. If you did this substitution method, you would go bonkers, I assure you, right? Because you would have to start substituting Z's, the Y expressed in terms of Z's, you know, into the X's, and go back and back and back and back and back. It'll just be too much. We wonder if matrices have an answer for you. Prepare to meet something interesting. 2 seconds ago, I gave you a bunch of z's in terms of y's, which is in fact a linear vector function of z's in terms of y. Notice I'm using the notation f to distinguish this function. So now you have a function that goes from R2 to R2, two y's to two z's. And I already know that I can express this in matrix form like this, right? So now I know that z, which is in fact a function of y, can be expressed in matrix form as the matrix A, which of course A is your matrix that you see over here, multiply the matrix Y, which is of course exactly what you see here. And you also saw in the previous slide the Y is in terms of x's, which you know is a system of equations going from R3, 3x's, to R2. Notice now I express Y as a function of x. I'm using a slightly different notation, G, right? So to show that Y is an equation in terms of x's. And once again, I can express the y's in terms of x's, and I do so by noting that it can be expressed in matrix form. Y is a matrix B, B is a matrix right here, times the matrix X. What somebody wanted from me was to express the z's in terms of the x's. Well, I could do it this way. What they're asking you to do is they're ultimately asking, you know that z is a function of y, and y is a function of x. So what they're asking you ultimately is to express z as a composite function of x. You can do it very easily. Here's how you do it. Begin with the fact that z is a function of y, and that's expressed in matrix form. But I know that y is a function of x. In fact, it's given by gx. And I know that y is in fact equal to bx. So here's your a that you already have from up there. But now you know that y is in fact equal to bx. Stick bx in, and now you notice that voila, you have the matrix A times the matrix B times the matrix X. And when I multiply these two out, it gives me a matrix C, which if I expand this out, allows me to write the Z's in terms of the X's. So I didn't have to put Y1s back in here. I didn't have to put the Y2s back in here, and etc. etc. I just had to take the matrix A, multiply with the matrix B, and I would have expressed C's in terms of the x's. Brilliant, right? So you can see that ultimately Z's can be gotten by A times Y, and then Y is of course B times X. So now you've understood that matrix multiplication in fact represents a composition of linear vector functions. You just celebrate by having, have some fun, have a scotch or a drink, listen to some good music. So how would you do this? I'll leave this as a possible exam question. Now, idempotent. So this is the analog of x squared, x cubed in numbers. A square matrix, only square matrices can be idempotent. A square matrix is called idempotent if when you multiply the matrix n times, and I hope you all have seen this notation before, this pi now stands for multiplication. So if somebody gives you a notation like this, it means now you're multiplying that creature n times. I forgot to put the I subscript here, although it doesn't matter. Who cares? Right? So multiplying the matrix x n times is the same as raising the matrix x to the power n. If it turns out raising the matrix to the power n, i.e. multiplying that matrix n times, simply gives you back the original matrix x. That matrix x is called idempotent. So you should verify these examples. You can click on these to go and see them in Wolfram, but obviously you should do them by hand, right? So x, this matrix times itself will be the same thing again. This matrix times this matrix times this matrix, same thing. This matrix Q, 4 to the power infinity, all the same matrix. So each of these matrices multiplied again and again and again and again by themselves will give you back the original matrix. Quick question. Is the zero matrix idempotent? Come on. Is the identity matrix or the diagonal matrix consisting of ones on the diagonal idempotent? You can work it out in 5 seconds. Transposes. Transpose means, and you should know by the way how to do this in Excel, right? Transpose means flip the number of the rows and columns. So you kind of want to be careful here. I had something with n rows, Nancy rows, kangaroo columns. When I transpose it, I use this notation. I used to like this notation until some undergrad, some students who went to Waterloo stopped me and they objected that this was not a transpose notation. I don't know what, maybe Waterloo needs to, I don't know, the kids I think Waterloo take things a bit too literally. You can use any notation you want. What stops you from using flowers? But in Waterloo, they use T for transpose. So if you're a Waterloo kid, okay, go ahead, use the T. Otherwise, I'm going to stick with the hair, right? X hair simply means transpose. So now you have K rows, N columns. And at first glance, your eyes start like, whoa, this looks exactly the same. They start to become blurry. But you notice slight subtlety. There's a 1 1 here, 1 1 there. But now you see how there's a 1K here. So the 1K element has now come down here. And of course, the N1 element has gone up here, right? So this was a linear function from Rk to Rn. This is a linear function from Rn to Rk. And I've shown them graphically over here so you get a sense of what's actually going on, right? To an example, by definition, transpose of the transpose is of course itself. So you should go home, get together with your friends, and you should work out under what circumstances will a diagonal matrix's transpose be the same, right? When are the two things exactly the same? Right? Rules. The best way to fail grad school, in fact, this course, is to ignore the rules in red. Bad things are going to happen if you make this mistake in Angela Millionaires course. I take no responsibility for what happens to you. Right? So, for a symmetric matrix X, the transpose and the matrix are one and the same. It's symmetric, right? So remember, the diagonal terms are not the same. The off diagonal terms are the same. This is really important, guys. Pay attention. I'm going to say this very slowly. The transpose of a sum is the sum of transposes. So you can see that when you open the brackets out, you can simply say x transpose plus y transpose. However, the when you do this on a product, be careful. You do not want to say that, so you don't want to say that this is the same as x transpose times y transpose. Rather, what you want to say is this is the same as y transpose times x transpose. The order shifts. So to make this point, draw this point home, here's a transpose of three things multiplied. When you quote unquote expand it, it's Z transpose multiplied by Y transpose multiplied by X transpose. Try doing this with four matrices, five. Try making groups of matrices in the middle. Try anything and make sure that you get this. The rank of a matrix. I'll come back to this in econometrics, um, but this is going back to lecture A. I'm going to abuse notation once again. I already know that a matrix, n by k matrix, consists of can be thought of as a collection of row vectors or as a collection of y vectors. So here what I've done is I've expressed row vectors. I'm sorry, I now call them w's. You'll see why. So here's row vector number one. I call it w1, w2, etc., etc. Right? And here are the column vectors, which I'll just call y, just for notation. How many row vectors are there? Well, there are n rows here, so there must be n row vectors, Nancy row vectors. So I ask you, if you were given n row vectors, right, each of which is, uh, you know what, I just realized that I should have said something about the relationship between n versus k. Okay, let's just forget k for 1 second. Right? If you are n row vectors, if there are n of those, how many of these n vectors are linearly independent? So of course, you can't have, right, the number of these n row vectors that are in fact linearly independent can be the maximum number, which of course is n, right? So you have n, a collection of n row vectors. So the maximum number of linearly independent vectors that you can have is of course n, which is not the same as the actual number of linearly independent vectors. Just in the same way, there are k column vectors. At most, you can have k of those be linearly independent, but the actual number might be less than or equal to k. Right? So the rank of a matrix is defined as, be careful, n is the maximum number of linearly independent row vectors. K is the maximum number of linearly independent column vectors. The rank of a matrix is the smaller of these two numbers. It's the minimum of the actual number of independent row vectors and the actual number of independent column vectors. Example. Here's a 3 by 4 matrix. It consists of 4 column vectors sitting in R3. Well, given the fact that in R3, at most, how many of these could be linearly independent? The answer obviously is 3, not 4, right? So I'm slightly modifying the last slide because the last slide I was careless because I wasn't careful enough to tell you what was the linkage between the number n and k. Was the number n bigger than k bigger than n? So since I didn't talk about n versus k in size, I just made this result. But now that I do have numbers, I realize that I have 4 column vectors, but they're sitting in R3 space. And it's physically impossible for all 4 of them to be linearly independent in R3, right? And you should ask yourself, why is that the case? Hint, you did this in a homework. The actual number of linearly independent column vectors is actually 3. So Wolfram Alpha is kind of cool in that sense. You can actually type stuff in. I was just going to say use bad words, but you can type vectors in. And you can ask Wolfram how many of those vectors are actually linearly independent. And spit out the answer 3. But how would you do this by hand on an exam? Right? You should think about this, right? Now you have a different interpretation. Now you have 3 row vectors, each of which are sitting in R4. And of these three row vectors sitting in R4, what's the maximum number of linearly independent vectors? Well, three, right? So how many of those are linearly independent? Three. So the rank of this matrix, this big giant matrix, was the minimum number of the actual number of independent rows, which is three. The actual number of independent columns, which is three. The min of three, of course, is three. And that's the rank. And you can click that link to see how it's done, Wolfram Alpha. Let's do it with a linear algebra. Sorry, excuse me. I've talked about adding matrices, multiplying matrices, quote unquote, taking them to a certain power, multiply by a number. What we haven't talked about are divisions. And that's because, sort of jumping ahead to inverse matrices, you know that when you divide numbers, it is the same thing as a multiplied by b to the power minus 1, which of course you know in numbers is exactly the same as b to the power minus 1 times a. You could do matrices, division with matrices as long as you're willing to interpret it this way. When somebody says give the matrix A divided by the matrix B, it is mathematically correct to say it's A times B to the power minus 1. B to the power minus 1, you may remember, is the inverse matrix. And you, of course, remember that the inverse matrix doesn't always exist. In lecture A, you know that it doesn't always exist, right? You know from lecture A that there are times when a matrix may not may not have the inverse. That will, of course, happen when, do you remember the answer? When we did this actually as a proof, the AT times 0, right? So you want to go back and remember how we do this. So because we don't always have the inverse exist, and also even if it did, it's not always true that A times the matrix is the same as that matrix times A. We tend not to use the words division for matrices. Going back to inverses, you can only do them for a square matrix. So here's a square matrix. Provided that it exists, provided the inverse exists, the inverse of a square matrix is another square matrix, which we call x to the power minus 1, so that when you take the original matrix, multiply by the inverse matrix, you get back the identity matrix. Okay? And you should pause at this point to say, well, why are we talking about this notion of inverses in the context of square matrices? Why can't we talk about inverses in the context of non-square matrices? After all, like if you took this little, if you kind of like, you know, well, if you stress the imagination a little bit, yeah, there could be maybe rectangular matrices. So why didn't I do this? Why do I always stick with square matrices? This is a really kind of a subtle question. It really forces you to think about whether you truly understand how matrices are defined. Right? So think about this question. And as you know, just because a matrix is square doesn't mean the inverse exists. Because from lecture A, you know that even if a matrix is square, it may not be invertible because its column vectors may be linearly dependent. We'll soon see how to compute the inverse of a square matrix, but to do that, we need to know how to do the determinant. Life sucks. How do you know that a matrix is invertible? You could exploit lecture A, so I'll leave that as an exercise. Or you could compute something called the determinant. And if the determinant is not equal to 0, the inverse exists, right? And if it is 0, the inverse doesn't exist. We're now going to see how to compute determinants. This is not going to be pretty. Here's a square matrix. There are countless ways of finding the determinant of a square matrix. In an exam, we don't care what method you use as long as you explain it and as long as it's correct. We don't give partial marks, by the way. Right? This is grad school again. Partial marks away. Never mind. I strongly suggest that if you're pressed for time, looking for jobs, you're in grad school and you suddenly you're stuck in a relationship, and now it's something has to give, right? Either you spend time with the beloved bae, or you do grad school. I suggest grad school, right? So if you're pressed for time and things are going wrong with your life, here's one simple method. It's called Laplace's, and I know that I'm not pronouncing this correctly. Last year, I had somebody spend 15 minutes arguing with me on how to pronounce Laplace. I'm not French, guys. I'm sorry. Okay? But using his technique by something called expanding the first row is pretty much fail safe, right? Or foolproof. Here's how it works. How do I find out the determinant of a matrix using Laplace's expansion method by the first row? Let's take a matrix that has exactly one element, Cx1, means one element. Well, you simply take the quote-unquote determinant of that one element. This is not the absolute sign. Be careful. So these borders are not referring to absolute values. They're referring to determinants signs. Okay? So simply take the determinant of that number, which of course is itself. This is a bit tricky. What Laplace says is if you always expand by the first row, what he said was take the first element in the first row, first column, and put a plus 1 there. See? So you multiply by plus 1. So plus 1 times x1, 1. And since in a 1 by 1 matrix, that's the only element, we stop. But now in a 2 by 2 matrix, once again, Laplace tells us, take the first element, which is x1, 1, pre-multiply by the number 1. So you can see there's a plus 1 over here, right? And then he says, multiply with the determinant of quote-unquote what's left over. So let me do that by like this. Okay. Actually, maybe not. So once again, take plus 1 times the element 1, 1, x1, 1 right here. Now imagine that since you're working x1, 1, you struck out, you got rid of the first row, and you got rid of the first column. See, get rid of the first row and column. You'll be left over with this thing element. And now what Laplace says is plus x1, 1 times the determinant of what's left over. What's left over, of course, is x2, 2. And then if you start with the plus over here, remember this, guys, if you start with the plus here, you must follow the minus over there. And then that would be your second element on the first row. Always begin by the first element of the first row, plus first element of the first row, first column, times determinant of what's left over, which is this right here. Always followed by a minus. The element of the first row, second column, multiply with the determinant of what's left over. So strike the first row out, strike the second column out, and what you're left with, of course, is x2, 1 right here. So if you got the hang of it, let's start with 3 by 3. Once again, plus the first element, which is x1, 1, multiplied by the determinant of what's left over, which is this 2 by 2 matrix right here. So take the determinant of this 2 by 2 matrix right here. That's what you see. Always followed by a minus sign, minus x1, 2 times the determinant of what's left over. So imagine striking out the first row, second column. What you be left with, of course, is these two numbers right here. They're right there. And those two numbers right there. That's exactly what you see over here, right? So plus first element, what's left over, minus second element, times the determinant what's left over, and then of course plus again. So plus, minus, plus. Now your plus x1, 3 times the determinant of what's left over, and what's left over, of course, is the determinant of this matrix right here, of these four elements. That's exactly what you see, right? So, couple of notes. In this one, I do a Laplace expansion by the first row, right? So again, first element plus first element times determinant of what's left over, minus second element of the first row times the determinant of what's left over. Well, what if I did a transpose? And you will notice subscripts have changed. The 1, 2 has gone down here, and the 2, 1 has gone up there, see? And if I again do by Laplace for first row, take the first element of the first row, which is again x1, 1, 1, times the determinant of what's left over, again x2, 2, minus this element right here, which is 2, 1, times the determinant of what's left over, which is this one right here. And if you compare the expressions, the two things are exactly the same. They have to be, right? Because you are transposing them, so the location of this number would stay exactly the same. Those things would get flipped, but since you are multiplying those things over here, even though you flip them, they flip, but this sign stays exactly the same. Hence, this is a general result. If you take the determinant of a matrix, it's the same determinant of the transpose of that matrix. Okay, the determinant of a matrix X is the same as the determinant of the transpose of the matrix X. And here's an example. You can see this in fact true. Now another result. Once again, we now do Laplace expansion by the first row according to the original matrix that you had over there. Right? Now imagine I swap rows. I swap the first row with the second row, right? So the second row becomes the first row becomes the second row. See? Second row becomes the first row becomes the second row. And again, I go by Laplace and say, so again, plus first element times determine what's left over, minus second element of first row times determine what's left over. And now you'll see that it's exactly the same as this, but with a minus sign. So this is a general rule. When you swap any two rows, what you'll do is the determinant stays exactly the same, but you'll change the sign. And for that matter, if you swap any two columns, you'll keep the determinant as it is, but have a different sign. Now we go to something, this is just horrible notation, but I didn't do this. But we have to do this anyway, right? 2 seconds ago, you saw that if you're asked to do Laplace expansion first row plus element 1, 1 times the determinant of what's left over minus element 1, 2 times the determinant of what's left over. So what some books do is, including our course and many econometrics courses, is they say, look, this is kind of horrible looking notation, x22, x21. Wouldn't it be nice to remind ourselves that this is in fact the determinant of what's left over, right, associated with element 1, 1? And wouldn't it be nice if we recognize this the determinant of what's left over, right, for element quote unquote 1, 2. So a new notation shows up. Instead of calling this x22, x22 is now called the minor element corresponding to x11. X22 is the minor element corresponding to x11. And we now denote this by M11. So life sucks. M11 is the same as x22. And now instead of calling this x21, we call this the minor element associated with element 1, 2. So this will become M12. The reason we do this is because it's sexier. As we know, mathematics is all about cool, sexy looks. So you don't want to say 1, 1, 2, 2, 1, 2, 2, 1. Ugh, this is a flow of the tongue. But this sounds so nice. 1, 1, 1, 1, 1, 2, 1, 2. Right? So you can see why some dead dude came up with this minor notation, because it makes things look sleeker. In that case, let's make sure that you can do the following correctly. You are expected in this course to calculate determinants of up to, I think we have done like 7 by 7 in the past, but I'll have mercy on your souls. So in your exams, let's say maybe, actually, I don't know, Tommaso might have something in mind. Let's do maximum 5 by 5 matrices as a determinant for the time being. Okay, let's use that notation to do Laplace expansion by first row of a 3 by 3 matrix. Now, you know the way to do this would be x11, first element, times determinants of what's left over, minus element 1, 2 times what's left over, etc., etc. Now, let's call this thing the minor element corresponding to 1, 1. See, it becomes sleeker, right? It's much nicer notation. Minor element corresponding to element 1, 2, minor element compared to element 1, 3. It just makes it nicer notation. Now, I strongly suggest that if you are struggling with math, you should use the method of first expansion by first row. It's pretty much foolproof, doesn't go wrong. But there are times when you might want to expand by a different row. Let me explain in what sense. First, let's do an example. Here is an example by 3 by 3 matrix, expanding by the first row. First element, times the minor element compared to for element 1 1, which is the determinant of the matrix left over 5 4 2 1 right here. Right. So it's pretty self-explanatory. You should work out these things on your own. Do the numbers is equal to 0. That means it can't be inverted. You can check that the answer is, of course, the same as doing Wolfram. And by the way, I strongly suggest that there are times when you can do it by first row, no problem. But there are times when you want to expand by second or third row. But that's a little bit tricky, and you should only do this if you're really sure what comes next is really clear. There's no confusion. Let's take a hard look at this thing once again. So you must have gotten the gist of it. Let me slow down a little bit. When I expand my first row, how did I start the signs? Plus, minus, plus. So what if I had kept going? I would have done plus, minus, plus, minus, plus, minus, plus, minus, plus. So notice that plus, minus, plus, minus, plus, minus, right? Plus, minus, plus. So you can see this because if you understood this, had I expanded by the first row, I would have done a plus first. See, the first term is called multiply a plus one. Plus, first 1, 1, right? Then a minus, then a plus. Okay. Had I expanded by the second row, by this thing I just showed you, you would have said plus, minus, plus, minus. So you know that the first term is being multiplied by minus 1. But if that's a minus, the next one has to be a plus. Next thing has to be a minus. Agree? And had I kept going, plus, minus, plus, minus, plus, minus, plus. So this would have been a plus. Next one would have been a minus. Next one would have been a plus. So you can expand by the first row if you want to, second or third, but you have to remember one crucial rule. Which sign do I begin with? Do I begin with a plus, minus, or a plus? Because once you get the first sign down, it alternates. So if this is a plus, next one will be a minus, next one will be a plus. Had you done by second row, the first one would be a minus, next one would be a plus, then a minus. Had you done by third row, you would have started by plus, minus, a plus. Easy way to remember this, of course, is notice the subscripts of the first term here, 1 plus 1 is 2, and last time I checked, it was an even number, I think. And the first term, if I add the subscripts up, 2 plus 1 is 3, which is an odd number. And this one, the first term subscripts is 3 plus 1, which is 4, which is an even number. So you'll notice that anytime the first term subscripts add up to an even number, you start the plus sign. Anytime the first term subscripts add up to an odd number, you start with a minus sign. Anytime they start with an even number, you start with a plus sign. So you get a general rule right here. Supposing I want to expand a 3 by 3 matrix by any row that I want. So this formula will work. And you should really map this equation to each of these three lines. Make sure you can do by the first row using sum, second row using sum, third row is sum. Make sure you get this, right? And you notice why this works. Minus 1 to the power I plus j. If the first element is 1, 1, this will be 1 plus 1. It'll be an even number. Minus 1 to the power even number gives you a plus 1, right? So you can see the minus 1 to the power I plus j is a very convenient and often used rule in graduate school for giving a plus for even numbers and a minus for odd numbers. And then, of course, you can multiply with the corresponding element and then, of course, the minor of that element. Now, not to be outdone, we know why we use minors, but because we didn't want to use literally the whole determinant in there, right? So, but somebody else comes along and says, could we make it even sexier? Because what that person was concerned with is they didn't like this minus 1 to the power I plus j into mij. So what they said was, maybe they got a paper published out of this, who knows? They took the I minus 1 to the power I plus j and the minor element right here, and then they call it Cij. Because what that does it makes it even cooler. Now you have Xij, and instead of saying, you just now say Cij. See, nice clean notation. It's in fact behind the scenes saying that, which behind the scenes is saying that ugly little matrices or determinants that you saw earlier. Some interesting things. We showed earlier the determinant of a matrix is the same as the determinant of the transpose of that matrix. We showed that if you swap any two rows, you'll get the same determinant with the opposite sign. If you swap any two columns, you get the same determinant with the opposite sign. This is a little bit tricky. When you want to find a determinant, you will get the same answer if you start to do the following. So here's what it means. Notice how the first column has a common quote unquote uh, number, multiplicative factor, see, 3. So I can pull the 3 out. Now this is really weird. This the first time people see this, they're like, what just happened here? You're not accustomed to, because when you see the number 3 going out, most people think that the number 3 was, so you understand why this is here. 3 times 5 is 15, 3 times 4 is 12. But you have to remember that I can do this because one column, pulling out of one column, not both columns. So I didn't I didn't extract the multiplicative factor 3 out of here. Right? So be careful. Okay? And then I noticed that the second row has a multiplicative factor of 2. So I can just pull that 2 out of just that one. I can do this. This is a legit operation when it comes to determinants. Right? You cannot do this operation for matrices. So instead of this, had this not been a determinant but a matrix itself, you couldn't have done this. But this is not a matrix, it's the determinant of a matrix. So you can do this, right? And so the answer, so whatever answer you got by doing this will be the same answer as if you first took the number 6 and then found the determinant of this. And I want you to go and verify the answer. So one more time. You can pull these multiplicative factors out if any one column or row has a common multiplicative factor, right? And you can do this because you're not working with a matrix, you're actually working with a determinant of matrix, which means that you have to be careful when some people go the other way around. So I know that this gives the same answer as that. But what if now somebody now became emboldened and now start to now go back in time? You want to reverse your steps, but they forgot how what was happening, right? So somebody who's never seen these steps before may start here, becoming emboldened. They might multiply the 6 in here, which is now, by the way, a legit operation because I'm multiplying by 6 everywhere, right? But that would not be the same as the, sorry, had you multiplied all elements of the determinant by the number 6, that would not be the determinant of what you were trying to find in the first place. So this is a nice little lesson in what that you can pull things out, right? So you're not putting the numbers out from all elements, from just either one column or one row. We're almost at the end. Uh, if I take a matrix right here, here's the determinant. If I now add so if I add now a multiple of this number to the second row, so I can add the number Ka to the second row. If I now add the number KB, as in boy, to the second row, the determinant I get is exactly the same. I wouldn't lose much sleep on this one, by the way. And this one, of course, would be important because you should be able to use lecture A to see why would having one row or column be a multiple of another row or column always give you a zero determinant. Come on, guys, you should know this, right? Why would having this row, which you know is a multiple of that row, guaranteed to give you a determinant of 0? And finally, something that will become really important, I know that I can compute determinants by using the minor notation or the cofactor notation. So I'm supposed to use, if I use the element ij here, I'm supposed to use the cofactor associated with the element ij, which means behind the scenes I should have to use the minor associated factor ij. But what if I accidentally use the wrong cofactor? Instead of using the ij, I use ji or ik or kl. I was going to say KLM, but that would not be a funny joke. Anyway, for example, instead of using the C15, right, I use C51. Here's an example. So I'm going to now compute the determinant of this matrix. I'm going to expand by the first row, but I accidentally use the second row's cofactors. So you can see that what I've done is wrong here, right? Because if I expand by the first row, this should have been x11, that's correct, but this should have been m11, not m21. And if I use the wrong cofactors, I notice that I get that the determinant is always going to be equal to 0. This is a general result. Use the wrong cofactors, and the determinant will always be 0. This is something we'll need for knowing how to invert a matrix uh, in our next lecture. Thank you.